Hi all, welcome back to my channel.
Welcome. Today, we're diving into combinational logic, a fundamental concept in digital systems. This session is brought to you by A. Sindhu Devi from Jerusalem College of Engineering. We'll explore the key ideas and applications that make combinational logic essential in computer science and engineering. Let's get started. Let's start by defining what a combinational logic circuit is. It's a type of digital circuit where the output depends solely on the current inputs. There's no memory involved. It doesn't remember or store anything from before. The output changes instantly as the inputs change, making it straightforward and predictable. This simplicity is what sets combinational logic apart from other circuits that rely on past information. Here, we see a block diagram of a combinational logic circuit. This kind of circuit takes multiple inputs and processes them through a network of logic gates to produce specific outputs. Unlike sequential circuits, it doesn't rely on memory or previous states. The output depends solely on the current inputs. This diagram helps us visualize how inputs flow through the logic blocks to create the desired result, setting the foundation for understanding more complex digital systems. Let's walk through the design procedure for a combinational logic circuit. First, we identify the input and output variables. This sets the stage for everything else. Next, we construct the truth table, which maps all possible input combinations to their outputs. Then, we derive the Boolean expression from that table. After that, we simplify the expression using Boolean algebra or a Carnot map to make it more efficient. Finally, we implement the simplified expression using logic gates. This step-by-step approach keeps the design clear and manageable. Here, we have a truth table showing two inputs, A and B, and an output. Why the output is 1 only when exactly one of the inputs is 1, either A or B, but not both. When both inputs are 0 or both are 1, the output is 0. This is the classic behavior of an exclusive OR, or XOR, gate. Our goal is to design a circuit that matches this pattern precisely. Let's start by identifying the inputs and outputs for our circuit. We have 3 inputs, A, B, and C, and 1 output. Why our goal is to design a combinational logic circuit where y equals 1 whenever at least 2 of these inputs are 1. In other words, the output should turn on only if 2 or more inputs are active at the same time. This step sets the foundation for how we'll build the logic that drives our circuit. Now, we move on to constructing the truth table. This table helps us visualize all possible combinations of inputs, A, B, and C, and their corresponding outputs. We count the number of ones in each row to see when the output Y turns on. Notice that Y is only 1 when 2 or more inputs are active. This step lays the foundation for understanding the logic behind our system. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. When designing any combinational circuit, we start by fully understanding the problem statement. Next, we identify the input and output variables involved. Then, we prepare the truth table, which lays out all possible input combinations and their corresponding outputs. From there, we write the Boolean expression based on the truth table. This expression is simplified using Boolean algebra or a Carnot map to make the design more efficient. After that, we draw the logic diagram with basic gates. Finally, we verify the output using sample test cases to ensure everything works as expected. Let's design a circuit with 1 control line, called C, and 3 data lines D1, D2, and D3. When the control line is high, the circuit needs to detect if any one of the data lines carries a 1. We know that only one data line will ever be high at a time. But when the control line is low, the output should always be 0, no matter what the data lines show. This setup gives us a clear way to control when the circuit responds to the data inputs. Let's break down the problem we're tackling. We have one control line labeled C and three data inputs D1, D2, and D3. There's a single output. Q. The rules are clear. When C is 1, Q should be 1 if any one of the data inputs is 1. But only one data line can be 1 at a time. When C is 0, Q must always be 0, no matter what the data inputs are. This sets the stage for how we'll design our logic. Let's start by constructing the truth table, the foundation for solving this problem. We know that no more than one data line will be active at a time. But when we simplify using a Carnot map, we treat any combinations with multiple active lines as don't care conditions. This gives us more freedom to simplify the logic. The table here lays out all possible inputs and their corresponding outputs, setting the stage for the next step in our process. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now we're ready for step 3, drawing the 4-variable Carnot map. We set the rows to represent the variables C and D1. Then, the columns correspond to D2 and D3. This layout helps us organize all possible combinations clearly. It's a crucial step because it sets the stage for simplifying the logic expressions that follow. Let's keep this structure in mind as we move forward. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about binary adders, essential building blocks in digital electronics. A binary adder is a combinational logic circuit designed to add two binary numbers. It's fundamental to how computers perform arithmetic operations. There are two main types we work with, the half adder and the full adder. Each serves a specific role in handling bits and carrying values during addition. Understanding these is key to grasping how complex calculations happen at the hardware level. Let's talk about the half adder, a simple but crucial building block in digital circuits. It adds two single-bit binary numbers, which we call inputs A and B. From these, it produces two outputs, the sum, labeled S, and the carry, labeled C. The sum tells us the result of adding the bits, while the carry indicates if there's an overflow to the next bit. This basic operation underpins how computers do arithmetic at the most fundamental level. Here we have a truth table for a basic binary addition operation. It shows two inputs, A and B, and the resulting outputs, the sum and the carry. When both inputs are 0, the sum and carry are 0. If one input is 1 and the other 0, the sum is 1, with no carry. But when both inputs are 1, the sum resets to 0, and the carry becomes 1. This simple table is the foundation for how computers add binary numbers. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the full adder, a fundamental building block in digital circuits. It adds three binary bits together, two inputs A and B, plus a carry input from a previous addition called sin. The full adder then produces two outputs, the sum bit S, which is the result of adding those three inputs, and the carry output count, which passes any overflow to the next stage. This simple circuit lets us add numbers bit by bit, handling carries along the way. Here we have a truth table for a full adder circuit. It shows all possible combinations of the inputs A, B, and carry-in, or sin. For each combination, the table lists the resulting sum and carryout, count. Notice how the sum flips between 0 and 1 depending on the inputs, while the carryout signals when a value needs to be carried to the next bit. This table is fundamental for understanding how binary addition works at the logic level. Now that we've looked at the truth table, we can use it to find the Boolean functions for sum and carryout. The tool we use here is called a Carnot map, or K-map. It helps us simplify the logic expressions by grouping values in a visual way. From this, we get the most efficient formulas for sum and carryout, the foundation for building reliable digital circuits. To build a full adder using combinational logic, we break down the problem into two parts, the sum and the carryout. For the sum, we need 4 3-input AND gates combined with 1 4-input OR gate. On the other hand, the carryout requires 3 2-input AND gates feeding into a single 3-input OR gate. This setup directly follows from the equations we derived earlier, translating theory into the actual circuit components we'll use. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's dive into the full adder built entirely with NAND gates. Remember, NAND gates are universal. That means we can create any logic function using just these gates. This slide shows the full adder circuit made only from NAND gates, highlighting how versatile they really are. It's a great example of simplifying complex designs by relying on a single type of gate. Let's dive into how a full adder can be built using only NOR gates. Remember, the NOR gate is a universal gate. That means we can create any logic function with just this one type of gate. Here, you see the circuit diagram that uses only NOR gates to perform the full adder's job, adding 2 bits along with a carry-in, and producing a sum and carryout. It's a neat example of how versatile NOR gates really are. Now, let's look at how we can build a full adder using half adders. This slide shows the logic diagram that breaks down the full adder into simpler parts, 2 half adders, and some additional logic. By combining these smaller building blocks, we achieve the full addition operation, including handling the carry input. It's a clever way to simplify complex circuits by reusing basic components. Let's break down how to build a full adder using half adders. First, we connect the 2 inputs, A and B, to an XOR gate and an AND gate. This gives us a XOR B and the product OB. Next, we take the output from that XOR gate and the third input, C, into a second XOR gate. This produces the full sum, a XOR B XOR C. Meanwhile, the outputs from the first XOR and input C go into a second AND gate. Finally, the outputs from both AND gates feed into an OR gate, which gives us the carry output. So, to make a full adder, we need 2 half adders and 1 OR gate. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about building a 4-bit binary adder. We do this by linking 4 full adders one after the other, in a chain. Each full adder handles 1 bit of the numbers we're adding. This setup is called a ripple carry adder because the carry output from each adder ripples down to the next. It's a simple, effective way to add 4-bit binary numbers, bit by bit, in sequence. Here, we see the inputs and outputs of a digital system. Specifically, a set of signals labeled A3 through A0 and B3 through B0. These inputs feed into a process that produces outputs named S3 through S0, along with a carry-out signal. This setup suggests we're dealing with a binary operation, like addition, where each input bit contributes to the final sum, and the carry indicates overflow beyond the 4 bits. It's a clear snapshot of how data flows through a basic arithmetic circuit. Let's break down how a parallel adder works. It starts with the first full adder, Fa1, which adds the bits A1 and B1, plus an initial carry, C1. This gives us the first sum bit, S1, and a carry, C2. That carry then feeds into the next full adder, Fa2, which adds A2, B2, and C2. This chain continues, each adder passing its carry to the next, until the last full adder produces the final sum bit and the last carry out. It's a neat, step-by-step process. Let's take a look at where the arithmetic logic unit, or ALU, plays a crucial role. It's the heart of microprocessors, powering everything from digital computers to simple calculators. The ALU is also key in digital signal processing, embedded systems, and even in designing specialized hardware like FPGAs and ASICs. These applications show just how foundational the ALU is across a wide range of technologies we rely on every day. Let's compare two fundamental building blocks in digital addition, the half adder and the full adder. The half adder takes two inputs and produces two outputs, but it doesn't handle any carry input. It simply adds 2 bits. The full adder, on the other hand, accepts 3 inputs, 2 bits plus a carry from a previous addition, and outputs 2 results. This carry input is what makes the full adder essential for adding multi-bit numbers, while the half adder is limited to single-bit operations. Let's look at a simple example, adding 2 binary numbers. We have 1011 plus 110. Using a 4-bit full adder, also known as a ripple carry adder, we get a result of 10,001, which is decimal 17. The key point here is the carry. It ripples from one adder to the next, passing along any overflow bit. That's exactly why this circuit gets its name. The carry ripples through each stage. Let's look at how to build a half adder using only NAND gates. We need 5 NAND gates to make this happen. This setup shows how those gates connect to perform the addition of 2 single bits. It's a clever way to create the half adder function without using other types of gates, relying solely on NANDs to do the job. Let's look at how to build a half adder using just NOR gates. You'll need 5 NOR gates to make this happen. This circuit shows how those gates connect to perform the addition of 2 single bits. It's a neat example of how a simple logic function can be created using only one type of gate, in this case, the versatile NOR gate. A binary subtractor lets us subtract one binary number from another. It works a lot like addition circuits, using an array of logic gates. The key trick is 2's complement. First, the circuit flips the bits of the number we want to subtract, then adds 1. This transformed number is fed into a binary adder along with the original number. So, with this approach, the same circuit can handle both addition and subtraction seamlessly. Let's talk about the half subtractor, a simple but important combinational circuit. It subtracts one bit from another, taking 2 inputs, A, which is the minuend, and B, the subtrahend. From these, it produces 2 outputs, the difference, which shows the result of the subtraction, and the borrow, which indicates if we need to borrow from a higher bit. This circuit forms the foundation for more complex subtraction operations in digital systems. Now, we're looking at the logic symbol alongside its truth table. This pairing is fundamental. The symbol gives us a shorthand way to represent a logical operation, while the truth table spells out exactly how it behaves with every possible input. Together, they're like 2 sides of the same coin, helping us understand and communicate logic clearly and precisely. This slide sets the stage for exploring how these elements work in practice. Looking at the truth table, we can derive the Boolean expressions that describe the system's behavior. The difference output is represented by an exclusive ORB. That's the XOR operation. Meanwhile, the borrow output happens when A is false and B is true, which we write as a complement and B. These expressions help us understand the logic behind the circuit's function. Let's talk about building a half subtractor using only NAND gates. To make this work, we need a total of 5 NAND gates. Each gate plays a specific role in handling the subtraction logic, breaking down the inputs to produce the difference and borrow outputs. This approach shows how versatile NAND gates are, letting us create essential arithmetic functions with just one type of logic gate. It's a neat example of simplicity meeting function in digital design. Let's look at how we can build a half subtractor using only NOR gates. It turns out we need a total of 5 NOR gates to make this work. Each gate plays a specific role in handling the subtraction logic, combining signals to produce the difference and borrow outputs. This approach shows how versatile NOR gates are. They can be the building blocks for more complex functions, even something like subtraction. Let's talk about why NAND and NOR gates are a popular choice for building half adders and half subtractors. First, they're universal, meaning they can create any logical function you need, including addition and subtraction. They're also cost-effective, since these gates are simpler and cheaper to produce than many alternatives. On top of that, they use less power, which makes them ideal for devices where energy efficiency matters. These advantages make NAND and NOR gates a smart, practical choice in digital design. When using NAND and NOR gates to build half adders and half subtractors, there are some drawbacks to keep in mind. One is propagation delay. These gates can be slower than others, which may slow down the whole system. Another issue is noise susceptibility. Interference can cause the circuit to behave incorrectly. So, while these gates have their strengths, they're not always the best choice. It really depends on what the circuit needs, balancing performance, cost, and power use. Let's talk about the full subtractor, a circuit that handles subtraction with 3 bits. It takes in A, the minuend, B, the subtrahend, and bin, the borrow-in bit. From these inputs, it gives us 2 outputs, the difference D and the borrow-out bout. This circuit is essential when we need to subtract binary numbers bit by bit, especially when borrowing is involved. On the slide, you'll see its logic symbol and truth table, which map out exactly how it works. From the truth table we just saw, we can derive the Boolean expressions that describe the circuit's behavior. The output D is the result of an exclusive OR operation between A, B, and bin. That's our sum bit. Meanwhile, bout, the borrow-out, is a combination of terms involving the complements and products of A, B, and bin. These expressions capture the logic behind the subtraction process in a clear, mathematical way. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, let's look at how we can build a full subtractor using only NAND gates. This is a great example of how a single type of gate can be combined to perform complex operations. By cleverly wiring NAND gates together, we replicate the logic needed to subtract bits, including handling borrow inputs and outputs. It's a powerful demonstration of versatility in digital design, showing that even with just one gate type, we can create the full functionality required for subtraction. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's look at how a full subtractor can be built from simpler parts. We use 2 half subtractors and an OR gate to make it work. Each half subtractor handles part of the subtraction, and the OR gate combines their outputs to give the final result. This approach breaks down a complex operation into manageable pieces, making the design easier to understand and implement. The diagram on screen shows exactly how these components connect to form the full subtractor. Let's break down how the first half subtractor works. It starts by performing an XOR operation on the input bits A and B at the same time. It uses an AND operation on the complement of A and B to create an intermediate borrow bit. Moving on, the second half subtractor takes the output from that first XOR and combines it with the input borrow bit using another XOR. The borrow output here comes from ORing the results of 2 AND gates. The final XOR output gives us the difference bit. Let's talk about the advantages of binary adders and subtractors. First, they're simple to design. Using basic logic gates like XOR, AND, and OR keeps complexity low. Next, they operate at high speed, especially parallel adders and subtractors, which handle calculations quickly. Finally, they're versatile. The same hardware can add and subtract, cutting down on extra components and making designs more efficient. This combination makes them a smart choice in digital circuits. Let's talk about the downsides of basic binary adders and subtractors. First, there's the carry propagation delay. In a simple ripple carry adder, the carry signal has to pass through every stage one by one. That means as you add more bits, the computation slows down. Then there's hardware complexity. More bits mean more gates, making the circuit bigger and more complicated. To fix delays, we use advanced adders like carry lookahead, but that adds even more complexity. It's a trade-off we have to manage. Let's talk about the parallel subtractor, a digital circuit built to subtract 2 binary numbers that are multiple bits long, all at once. Instead of subtracting bit by bit, it processes pairs of bits in parallel, which makes the operation much faster. It works by subtracting corresponding bits simultaneously, using borrow signals to handle cases where borrowing from the next higher bit is needed, much like how addition circuits use carry signals. This approach speeds up subtraction significantly. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's break down how a parallel subtractor works. It's basically a set of full adders wired together, but instead of just adding, we subtract by using the 2's complement of the number we want to subtract. First, we get the 1's complement by flipping all the bits, then add 1 through the carry input to get the 2's complement. Adding this to the other number gives us the subtraction result. This process moves through each full adder, with the final carry bit completing the operation. Let's look at the advantages and disadvantages of the parallel adder subtractor. It's faster than a serial version because it adds or subtracts all bits at once, so the time doesn't depend on the number of bits. It's also less costly and gives output in parallel form. But there's a catch. Each adder waits for the carry from the previous one, causing delays that grow as the number of bits increases. This propagation delay is a key limitation to keep in mind.
Thank you for watching my channel. Please do like, share and subscribe my channel.